Okay, this talk is optimal data loads. And just to give you an overview of this talk in a nutshell, I always think it's always good at the outset to let people know, where the talk is going, right? Your time is valuable, and I want to make sure if you're here that you're learning things, right? This is really all about how best to load data into Postgres. It's characterized on the schedule as an intermediate talk, but it's definitely beginner friendly, right? And I would characterize it as kind of a tips and techniques talk with examples, with timings. It's really one example that we actually evolve out, so you can get a good comparison of some of these tips and techniques and how valuable they are, relatively speaking. We're going to talk a lot about the copy command. We're going to talk a lot about how network latency comes into play often in performance on data loads, as well as things you can do around DDL and TCL, right? Commit frequency. That will also improve the data load process for you. The slides and the scripts are in a GitHub repo. You can see it right there. It's in my GitHub account. So you can access them there. Just a little bit about me, so that, it's always good in a talk, I feel, right, just to give the little bio slide so that people know more about your background. We're formed by our experiences, and we form biases and beliefs based on that, right? So for me, my current role is data engineer at something called the History Lab at Columbia University here in New York City. And the History Lab, basically, you can click on the link. Actually, we check out the slides later. It's an interesting group. It's really, they take documents and turn it into data, right? So it's really data science applied to history. And we do a lot of database work. Actually, we maintain a database called the FOIA Archive, which is the world's largest database of declassified government documents. And we store metadata and even the text of these documents in Postgres, amongst other platforms.
Would you say you're the opposite of WikiLeaks?
Well, that's right. Yes, I would say that is actually a very fair classification, because we only.
They were early Postgres also.
Yeah, that's right. Right. That's absolutely the case. But no, in terms of the History Lab, it's way different than that. We only deal with documents that have been declassified. And actually, not to go on too much about this, but our PI, my boss, a fellow by the name of Matthew Connolly, he's going to have a book coming out at the end of this year called The Declassification Engine, really, which talks about a lot of the issues associated with the problems that we're trying to tackle at the History Lab. And it'll be
very timely topic.
Exactly right. But the stack that I work with these days is largely Python, SQL, a lot of AWS and shell scripting. And I've been working with Postgres since 2015, working with relational databases. I started working with Oracle a really long time ago, as you can see there, right? 1988. Career-wise, I've done a variety of technical, managerial, and also product roles. But in this phase of my career, I've moved back to a more technical role, right? Because I really like the hands-on aspect of things. Feel free to connect with me on LinkedIn if you'd like. You could also check out my other work on GitHub, as well as I'm on Twitter. I don't tweet that much. I'm more of a consumer, but occasionally I'll tweet, like, let's say, about this conference. Also, too, just one, I don't know if it's a tick or how you'd want to describe it. Throughout the slides, I call Postgres, I refer to it by its name, PostgreSQL. But throughout the talk, I'll just call it Postgres, right? Just a few preliminaries before we actually go into the tips and techniques, kind of set the groundwork for looking at the tips and techniques. There is just as we already had, right? Feel free, if there's anything that comes up during the presentation, to ask questions, right? If it's going to be something that we're going to cover, like in a slide or two, I'll take the prerogative to say defer and come back to it later. And then also too, we'll have a question and answer period at the end of the talk, right? And comments too, as well as if people want to make comments. So let's get down with some of the preliminaries, right? First of all, this talk is called Optimal Data Loads, right? So I think we should talk about first what it is we're optimizing, and then what a data load is, right? Just for level setting purposes. And as often the case, and as primarily I think is the case in the database world, right? We're optimizing for time, looking to minimize load time or program runtime, however you want to characterize it. But also in this talk, I put pretty heavy emphasis, or in this work, I put very heavy emphasis on optimizing your time, right? Developer time. How much time it takes to develop these scripts and procedures, as well as how much time it'll take to maintain them if something goes wrong, right? And that is actually a very key component of this work, as you may already agree. Now, in the brief description in the conference schedule, I say a data load is the L in LTL and ELT, right? It's a little bit of a, well, let's go and look and see first what ETL and ELT is, and then we can actually define what a data load is, and then move on to looking at how to make it fast, right? So if you will, ETL is really the first term that was introduced in the data warehousing world to describe the process of getting data into a data warehouse, right? So I remember, reading these books by people like Ralph Kimball and Bill Inman in the early 90s, right? And they would introduce this term ETL for extract, transform, and load. In the extract component, right, you're getting the data. Transform, you do, maybe a mapping, a restructuring of the data, maybe validation of the data, and then load is basically storing it in the database, or in those days they called it a data warehouse. Okay, and we still use that term today, but a few years after this term was introduced, you actually had people start using the term ELT, right, where you actually did the load before you did the transform. And I think there are basically three reasons why you saw this happen, right? Somebody didn't just invent the term to come out and describe a different kind of process, right? This is actually what people were doing, myself included, but it wasn't necessarily yet called ELT, right? I think there are three reasons why this became big. Does anybody want to? What would you think? What do you think one of the reasons is, maybe?
For one, I think it's a matter of speed. So you could get the data loaded rather quickly into the database as is,
Yes.
and then from there apply some business logic, something that perhaps the ETL tools themselves sitting in the middle layer didn't provide that capability or slow down the process to such extent that it was easier to go with the ELT instead.
Yes, I would agree. I agree with that. I would actually phrase it maybe a somewhat different way, right? I think one of the things is, and you didn't explicitly say this, but I take it to be what you mean by this, right? Is that SQL itself is actually a very good language for doing transforms, right? It's set-oriented, it's declarative in nature. It's much more flexible than trying to do that kind of work in Java or in Python, in most programming languages. So one is that benefit of being able to do the transform in SQL. The other aspect that you hit on, which I think is very key, is that databases in those days, as I might have mentioned, I was working with Oracle, right? So they had a high-speed loading tool called SQL Loader. Postgres has something a little bit different. It has the copy command that we're going to take a look at, right? And I think one function for that was the ability to now just script out these loads, right, and use the high-speed load capability, right? So I think that is another factor. And a third factor that I find to be the case, I'm not sure people were necessarily thinking this way back then. I wasn't, but over time I've come to appreciate it, is that if you are actually loading your external data, then if you have it in some sort of staging table, right, which is something that is typically done, there's a lot of value to that, right? Because when there are problems with the data, then you can interrogate it with SQL, right? And it makes it much easier to handle as opposed to, a tool that sits outside that maybe, leaves the data in files. It's just much easier to deal with. So I think it's those three reasons. But why am I talking so much about these processes? Well, we wanted to define the data load, right? But I also, obviously I think I'm interested in the transform component, right? There's a lot of interesting aspects of the transform. We're not going to talk about it today. But the thing that I think bears mentioning in this context is that load and transform, here they're all separate boxes and they're neatly divided, right? They actually have kind of, if they were planets in a solar system, they have a gravitational effect on each other, right? And it's not always quite as neat as clean as boxes where you do all the transform and then you load it. So that is a takeaway I would take from these slides. Now, let's just focus in on load because we just need to simplify and look at the load for the purposes of this talk. And so here we have what we're talking about in terms of data load. We have something we're calling external data. We have a load program, and then we have Postgres. So it could be even another DBMS in another context, but we're all Postgres users here. We're saying external data is data that's not in Postgres. It's from some sort of outside source, right? So there is this process of getting it into the database. In certain cases, you may think of load procedures. You may have something in a different schema or in a different cluster, and you need to get the data into a data warehouse or some sort of analytical database, right? Here we're going to really focus on where that data is actually not in the database. The other thing about data load that we'll say is that in practice, it's something that often needs to be rerun, right? We call it refreshing the data. Often you're bringing in data from an external source, and it's running, maybe daily or weekly or monthly. You're getting updates. So there's this aspect of refresh. So it's not just a one-time process. Now, when we go into our examples, which we're going to start doing now, we even constrain this definition a little bit more. Our external data, for the purposes of the examples, will be an input file, right? And we're going to look at something that's in the limited text file. It's in CSV format, right? It has a UTF-8 encoding, right? We're looking at a kind of a simpler space. In our load program, well, we'll either look at a Python script or even in certain cases, we'll look at just using PSQL commands for loading the data into a specific one database table, right? So it's simplified. Granted, it's a very simplified context, but it gives us a way to look at these techniques for making the loads perform more quickly. Now, for all our examples, we're going to use the same input file. It's basically a set of companies' data. Again, it meets our characteristics of being in UTF-8, being CSV. It's pretty big, right? It's 295 megabytes. So that's one thing you will not find on the GitHub repo is this data file, right? It's got about 2 million records in it. It's got about 10 data fields. It has an ID field, so it has a primary key field, right? And it's actually a subset of public open data published by an organization called Glyph, which is, yes, question?
Could you define what is that subset, like how you choose that? Is it a subset of the total number of records in Glyph, or is it a subset of just the fields that is being published?
Okay, yeah. So it's basically a subset of both. If you're familiar, I don't know, are you familiar with the Glyph data?
No, I'm
okay.
not, but I'm just interested in how, 2 million records, right? Is there more data, more companies out there?
Yeah, there's actually more data that you can actually get from Glyph. It's not necessarily related to different companies, but different details about the company, including ownership hierarchies, including information about securities that they've issued, so on and so forth. And I was thinking, hey, can we do something a little bit more complicated for this talk? But it just turned out to be a little bit unwieldy. In fact, this data is data that I use in, I built a system before I started working at the History Lab called LEI Smart, which does basically data reconciliation, data audit, and it's a service that can be used by banks and other financial institutions that have regulatory reporting to make sure that the identifiers that they're using in their reporting are in fact the ones that are in sync with the data that's published by Glyph. And so a lot of the tips and techniques, I think all the tips and techniques, in fact, that we're going to review in the talk are ones that I used in that system and also elsewhere, including in my work at the History Lab. But yes, the data is bigger. In this case, the company's data set is this size. It's actually grown a little bit since the time that I put this test set together. And the number of fields is much reduced, right? They actually have hundreds of fields about companies, including different names that may go by, different addresses, and so on and so forth. But if you go to that link, you can actually find the data itself if you're looking for that sort of data. And it's interesting for this, this kind of timings results. I almost used that term benchmark, and I'm going to get back to why I didn't do that in 1 minute. So if you look, we're just going to load into one table, right, for simplicity's sake, so we can, we only have, a certain amount of time for this talk. By the way, anything that you see with the file reference, that is something that's actually in the GitHub repo, and that's the name of the file. So it's just a company's table. It's got a primary key. It's got a few text fields, a few date fields, right? It's pretty simple and straightforward. And we're gonna show some timings, and so it's good to actually show what the hardware environment is, right? We call a local environment. This is where the developer, in this case, right, is doing their development. You can kind of think of it as a client, but when they're doing their development work, they're also running the database local, right? And that kind of plays a pretty big part in our story. And then you have a server. This server is running on AWS, right? And you see the characteristics. And then the software, we're running on Postgres 13. Python examples both use recent versions of Python. Scicop-G is basically the database adapter between the one that's used almost, I don't even know what the percentage is, but overwhelming amount of time when someone has a Python program and is connecting to PostgreSQL, they are using Scicop-G. Let's think of a specification for this load script, right? Just to kind of set up the story here. We're going to say the load must run in less than 12 minutes, but the quicker the better. We're going to try to get this as fast as possible, right? It's going to load 3 times a day, so every 8 hours. And the load is going to overwrite the existing content. And since this is reference data, we're just using it to do lookups on the company data. It's really only read-only once it gets loaded, right? Which also is going to be a component of our story as we look at examples. I want to say one small thing about timings, right? Maybe it's not even a small thing. One is, and you heard me a minute ago, I almost slipped myself. I'm calling these timings not benchmarks, right? In the database world, benchmarks historically have played a big role, right? Maybe more so than in any other area in my opinion at least, any other area of computing other than high performance computing, right? Especially if you go back in time, there are the TPC benchmarks. And if you go back when relational databases were used, primarily for transaction processing loads, a lot of the vendors in those days, everything was really commercial software, like the Oracles or the Microsofts or what have you, would publish these benchmark results, the TPC benchmark. Originally, it stood for Transaction Processing Council. You can actually go to their site. They don't call themselves the Transaction Processing Council anymore because over time, the use case for RDBMS has expanded dramatically, right? You first had data warehouses, then you had more analytic use cases. So if you go to the TPC benchmark website, you'll see, they have even recent benchmarks that they've introduced for AI and other kind of database-oriented workloads. So it's pretty cool. And if you go there, I encourage you to take a look. They publish a spec of what you need to do in order to actually do a TPC compliant benchmark. And it is very, very extensive, right? And as you might imagine, you're very, it's very specific in how you can configure things, right? Because you want to do and, have something that does an apples to apples comparison, right? It's a lot of work, right? When someone blogs and they actually show timings, right, they don't go to that level of detail that is done in the TPC benchmarks, and they can't, and they really shouldn't, right? It's just not worth the time to do it, right? So the reason why I say this is that, like a month or so ago, someone who's big in the Python community, a fellow by the name of Miguel Greenberg, who has actually developed the Flask framework, which is a web framework that's used in Python. It's very, very popular. Published on his blog, basically a blog post that was like, oh, ignore all benchmarks. And in this case, he was looking at a case where someone was trying to benchmark async performance of web servers, right? And he showed that, if the person, had applied a certain patch, the results would be different. If you do different things, the results would be different. Best you just go and use the framework that you like, and don't worry about benchmarks. Well, there's something about what they were doing in those benchmarks too that bears mentioning. They were actually looking and trying to measure very small timing differences, or relatively small timing differences, as opposed to what we're going to look at here, right? And in that case, I can see it's very hard as an individual to control all the different factors that can be impacting the timing of something, right? So you really need to be humble, right, when you do even timings, and you need to tell people, hey, your mileage may vary when you try these things. And in fact, what I've done in the repo is that if you have a data set that you want to try these tips out on, you can actually clone the repo, download it. You can make some small modifications to scripts, and you can actually run and see what the results are for you, because your mileage may vary, right? And so the other thing I would say is that, hey, in this talk, we're really looking about things that can be dramatic game changers, right? They're kind of like eternal truths. Just like if you have a table with a primary key ID and most of the queries are going to be against that ID, right? You know that you need to have, well, if it's a primary key, it will already have an index by the fact that it's the primary key, right? But you know you need that field indexed, right? And that there'll be tremendous performance differences between doing the equality query on a specific ID for a table that has 2 or 3 million rows versus it doing a full table scan, right? That's kind of that's an eternal truth, right? It's true across versions of Postgres. It's true kind of almost regardless of your configuration. That will be the case, right? Things change, and those numbers can change dramatically. And if you look over time, things that 20 years ago were using the index, if you look at the query planner, may no longer be using the index if the table is smaller, because full table scans and SSD and other things have come along, right? But that is still the case, right? And that's kind of what we're looking for here, right? So enough said about that, right? So now we're finally getting to the tips and examples. I just want to see where we are. 3:10. Okay, we're doing pretty well time-wise. People do development of Python? Okay, there's a lot of Python people here. Even if you're not, though, you'll see and understand this program. So let's actually kind of create a little story, right? So we know we want to load this data in. There's a developer. Let's call him Don, for the sake of the story. Don, the developer, who's tasked with loading this data that we just showed you into PostgreSQL, right? And so Don decides to write a Python program. And even if you're not a Python person, you can see what's going on here, right? So it's a simple insert statement. Don's program is connecting to the database. He's actually auto-committing, which is interesting, right? And something we'll come back to. And then he's just doing the most simple thing you can imagine, right? Which is often the right thing to do when you're doing development, is that he's opening the file, and then he has a cursor. He declares a cursor, and he's basically executing, right? And he's inserting row, 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 and that's it, right? And so then what happens? Well, he's doing his development local. Everything is local on his Mac, right? That we showed the configuration for, right? Which is my Mac, right? And so when he runs this with the 2 million plus rows, it takes and the index and everything else, it locally on his Mac, it takes 9 minutes and 15 seconds. Okay, well, he needs to get this completed in 12 minutes, right? So he's like, oh, okay, I'm in pretty good shape, right? So, time goes by, the release cycle progresses, and the, QA person comes by and asks Don to run his program so that the data can be loaded to the QA database for testing purposes, which is on AWS, right? So Don kicks off the script and kind of goes, does some errands, and then he comes back the next day, comes back to his desk, and he looks, what happened? This program now took 7 hours and 11 minutes to run. No, something's wrong. He doesn't actually believe that result, right? So it ran to completion, but gosh, if we're running this 3 times a day, like Don's program is running almost nonstop, right? It's running like 21 hours a day. And so if you're Don, and Don reacts, let's say, like I would react, like I would have different feelings, right? Don is not a database expert, right? He knows about tables, he knows the insert and so on and so forth. He thought he was fine, but he is not. He's not. And so if I was in his situation, I would have a feeling, I'd be a little panicked, right? Because all of a sudden I thought everything was okay. There's something going on, right? And then you'd probably be like, I don't know, angry is the right word. You'd be indignant almost that this has happened, right? At least I would be. And I would look for reasons to explain it, reasons that maybe exonerated me from any sort of responsibility in the process, right? But thankfully he didn't go up into Slack and put a message into Slack to the whole team saying that, hey, we need to cache this data. We need to introduce a middleware layer between the database and the program or something crazy like this. No, what he did is he went to talk to Debbie, the DBA, right? And Debbie, the DBA, and he asked her, hey, were you doing anything to the QA environment that would cause such a thing to happen? And so Debbie asked to take a look at his program. And even though she doesn't do Python, she could see, because she's seen programs in the past, maybe in C, Rust, Java, any language that you might imagine, that are kind of this nature, right? Where it's doing one insert at a time, right? And so she recognizes that there's going to be some performance problems here. So it's not surprising what Don is seeing, right? And the number one performance problem in this is network latency, right? It's the dominant factor causing that degradation, right? And you can think about it, if you do a back of the envelope calculation, right? Every time, Debbie knows, every time you execute, right, you have messages sent to the server from the machine where the program is running, right? And even if you have, this case, the network is not bad. It's not a high-speed plane connecting the machine, right? It's going across the internet. But even if it's taking 20 milliseconds, right, which is not that much, right, in network latency for each row, you can do the math, right? And if you do it over 2 million times, it's going to be, it's going to end up to be about 7 hours worth of time, right? If the data set here was only 5,000 rows or something, right? Don's program would look a little sluggish loading into QA, right? But it would only take a minute or so still, right? You wouldn't see the problem. You have to have a bigger data set for these problems to really manifest itself in a terrible way. So she sees that as one problem. There's also the other problem here too, as well. It can be a significant problem, but it's not as big as a network latency issue, right? And that is the commit frequency. Here, Don has set his program to auto-commit. But you know, you're running this load program. You really don't need to commit every single row, right? In fact, you don't have a procedure if something, you know, happens with the data, right? You'll just rerun the procedure. So that's another thing where, you know, instead of auto-committing, which you actually have to explicitly set to true for in PsycopG, by the way, you could just commit at the end, right? And you'll get a performance increase there, right? And then the other thing is really, you know, you're sending an individual insert statement each time. It has to be parsed. It has to develop an execution plan. So there's parsing and execution overhead, right? That adds up too as well. But in the overall scheme of things, they definitely go in this priority order. So there are things that Don could do to his program that, you know, that could incrementally improve the program. But Debbie suggests he look at something else, right? Debbie suggests that he look at copy, right? And she explains to him that copy is the fastest way to move data between the OS and Postgres, right? And that it's optimized for a large number of rows. In fact, it manages these three problems that we've just seen, right? The network, the communication, and the execution overhead. It's available as a command in Postgres, right? But there's also, too, if you dig down into the Postgres documentation, you'll see that there's actually a message protocol for copy in Postgres, right? In other words, it's not as if someone wrote copy and then behind the scenes is doing a lot of inserts. No, it was developed specifically for this use case of loading data directly into a table, right? Postgres itself uses it, for example, in PGDump, you know, the backup utility. And it's accessible. You can access it in PSQL. You can access it in Python too, as well. In the PsycopG, you can actually use copy from. So it seems like it's a pretty good bet. She points them to the documentation. You can see here, you can actually both bring data into Postgres using copy. You can also export data out, right? And there are different formats that are supported. There's CSV format that's supported. There's a text format that is the default format with tab separated values. There's also a binary format, which is largely used in Dump. And then there's other things that you can specify, including the encodings, how you handle nulls, whether there's a header or not, right? Simple stuff. So Don goes back to his machine, and he says, hey, let me give this copy command a try, right? In this case, it turns out in the CSV file, the columns are ordered in the same order as the columns are in the table definition, so he doesn't even have to specify the column names, right? So he turns on timing, and he sees, hey, on my local machine, truncates the table, and then he runs it. 51 seconds. That's pretty good, right? That's a 10x. That's roughly a 10x faster performance, right? And that's not even, you know, here when you're running it local, you don't even have this gain from the network, reducing the network latency, right? So what happens? He needs to reload for QA again, so he's going to try to use copy to reload. And wow, you would think it'd be slower, but it's faster still, right? And that, over the original version where he was doing a row at a time, that's like enormously faster, right? Now, you know, again, your mileage may vary. You can try this with your own problems if you like, but he got a tremendous speed up with due to Debbie's guidance, right? And you can see the copy is even faster on the DB server, and that's because the DB server itself is a more powerful machine. And in fact, it wasn't really a network problem per se. It was really not really understanding the network latency issues that were being introduced by the mechanism that was used to insert data in, right? And so those problems were all basically cleaned up by copy. And you may ask, hey, what will happen if we run it directly on the DB server itself? And we get another gain, right? But it's not as dramatic as what we saw just by switching over to copy, right? It goes down to 21 seconds, right? Which is about 1.5 times faster. So this is all good stuff, right? Now this improvement we show is mainly attributable to the input file on the server, right? If you have to R-copy the file up to the server, a file that size, you know, it's going to take in this environment, it would take more than just a few seconds, right? It would take about 6, 7 seconds. So a lot of this can be attributable to the file already being there. There's also something too, when you look at this, there's actually a difference between, the documentation makes this out to be a bigger thing than it is. There is a copy command, and then there's a / copy command. You'll generally use the / copy command, right? The copy command is only available to you on the DB server, and only available to you when you're the Postgres OS user on the DB server, i.e., on the user account that actually has started Postgres. It turns out that even if you happen to be on the server, there's basically no difference in performance between the two. You can use /copy there. So if that's confusing to you, don't worry about it. Use /copy if you're using PSQL. If you're using if you're Python and you're using scopg, you can use that method that I referenced. If you're using another programming language, right, you'll be using a database API, a database adapter. A good thing to look for is, does it support the copy command, right? They don't all necessarily do so. I think the ones that will be most popular for your language will do so, right? But that's something that you can look at as a kind of a checkbox item when you're evaluating database connectors. Now there are some shortcomings to copy. Just want to make sure we're okay. We're good. One is that it must load all the columns in the input file, right? And you know, the data types have to match up with the Postgres data types, right? There's no way to apply functions to actually transform data via just pure copy itself, right? An issue, this could be at times, it can be either positive or negative actually, right? Copy stops at the first error and then rolls back, right? That may be okay. I think in our scenario, where we're loading the data, especially now that we're loading the data in a relatively short period of time, right? I actually think that that's fine that it does that, right? But your scenario may be different. The data set might be much, much larger. There may be other dynamics involved, and you don't want that to happen, right? You'd like the data load to continue, and that errors could be pushed off somewhere else, right? So that can be a little that can be an issue, right? Another issue that pops up which I have dealt with, right, is the fact that if you're not using CSV, let's say you're using tab separated values, and you have a text field. Wow, I'm down to 10 minutes already. Okay, then the copy command can cause you problems, right? Say you have a memo field in your database and in your data file, and that memo field has a tab in it. It could actually mess up copy, right? It's the same thing with embedded delimiters, backslashes, and carriage returns. These are things that are gotchas. And then the other thing is that the copy command itself must fit on a single line. So addressing copy shortcomings, there's a couple of ways to go about this, right? Often what you can do, especially if you're familiar with these tools, right, is that you can pre-process the file with command line tools like tr, sed, and awk, right? Another way to go about dealing with it, and a way that I use quite frequently, is using a staging table, right? That eliminates a lot of the problems. You load the entire data into a table. The table is set up to have the same number of columns that's in the CSV file. All the fields are text fields, right? You very rarely will get errors, and you very rarely will get errors in that case, right? It works out really well, and you could do a whole talk on staging tables. The other thing to potentially take a look at is PG Loader, right, which is a utility developed by Dimitri Fontaine, who is pretty well known in the Postgres community, wrote The Art of PostgreSQL. I'm actually a big fan of his overall. It's a great utility if you're actually migrating databases to Postgres. You can also use it in lieu of copy, especially if you like the way it handles errors. It's much more, it has much more flexibility. But with that flexibility, it's more you have to install the software, and it's more complex to use, right? So I've used it for migration. Haven't used it as much for copy because I'll end up using a staging table. So, now Don is really into Postgres because, hey, this thing is running in 30 seconds. He feels like he's a star now, although Dibby was the one who set him straight on this, right? So he's getting Postgres weekly, which is something that I think everybody should get, right, who's really into Postgres, because you just learn so much because it does a great job of aggregating interesting blog posts, right? And he gets one where it says, hey, you can actually get even further performance improvements by dropping indices and primary foreign key constraints, doing the copy, and then re-enabling the primary key or recreating the indices, right? So we're at 21 seconds right now. What happens when we do drop, copy, and recreate? Well, we do gain, right? But it looked like it's only like 1.2 times faster, and the copy itself goes down dramatically, but the primary key creation again afterwards eats up a lot of it, right? So you gain, and your mileage. And here your mileage may vary because you may have multiple indices. You'll have to try for yourself to see, right? For me in this case, it was only 1.2 times faster, but it could be different, right? And then the other tip that he saw was using unlogged. So let me quickly go through that. It's an attribute of tables that's been available in Postgres for a while. You can create a table as unlogged, or you can alter a table and make it unlogged. And what happens is that unlogged tables are not written to the write-ahead log, the wall, right? And so there's two ramifications to that. DML, right, any sort of insert, update, or delete, is going to be faster against an unlogged table, right? But there's a big warning that comes here, right? The unlogged tables, they're not crash or standby safe, right? If you have an unlogged table and your instance crashes or you try to use a failover, you will find that that unlogged table is truncated. It's got no data in it because it was never written to the write-ahead log, right? So the bottom line here is that you really have to think through your application before using it. Now, if we think through our, toy application here, we're loading this data 3 times a day. We're basically saying, hey, it's going to load or not. If not, we'll fix it, so on and so forth. It actually does seem to be a good candidate for unlog. So let's take a look at what happens here. We go from 18 seconds to 13 seconds. So again, our gains are smaller here, but they're gains nonetheless. And if you look at the copy, it runs at pretty much the same time as it did without it being logged, but the primary key create time goes down pretty dramatically. And then don't bother with this tip if you think you're going to set the table unlogged, run the load, and then set it to be logged, right? That's actually going to take you more time because when you actually turn logging back on, it's actually a pretty time-consumptive operation, right? So the key takeaways, 5 minutes, and we'll have time for questions, great. Use copy whenever possible, my advice, right? May not always be possible, but when it is. And even if it isn't possible, you can look at this, drop, load, recreate the indices, primary and foreign key constraints. If appropriate, knowing the ramifications of it, you can consider no logging. If not using copy, you want to look to minimize the network latency, right? Commit frequency, and parsing and execution overhead. Now we can go back and look at Don's original Python program, and one of the things I would say is that there may be times because you're responsible for a program that was developed by another group or maybe outside your company altogether, right? You can actually still get good performance gains by moving it either onto the database server, if you can do that, if you can get away with it, or to a machine that has a high-speed interconnect to your database, right? Because you could see how much of a difference it made, even Don's simplistic program, by having too much network latency, right? So that's a big thing. If possible, develop with a DV environment similar to production. Don didn't have that available to him, and that's why he got panicked at that point and had to go see Debbie, which actually turned out to be good. He learned a lot in the process. And then one thing that was done that he did well, right, was spend time identifying the actual problem source as opposed to, throwing up your hands and going to another solution, right? These are not load-specific things. These are general guidelines. We didn't cover what you do with triggers. We didn't cover parallelism, right, which really is only applicable when you're using kind of a shared nothing parallel architecture, in my opinion, so something like Citus, Greenplum, or maybe something with timescale. We didn't look at the Postgres configuration options, but when you look at hints for doing that, it's usually around the wall, right? And so unlogging kind of is a separation for that. And we didn't look at the advanced methods for bulk inserts in PsycOpG, right? With that, I open up to questions and comments from people. Yeah.
One area where, if you could go back 2 slides for me.
Yes.
Yep, right there.
Okay.
So one of the things that I was kind of thinking on the ELT type of approach,
Right.
you might be able to use the no logging if you're using a staging table.
Totally.
So, you know, who cares if
Totally.
Even if it fails, you're probably looking at restarting it anyway.
That's right.
And then once it goes and tries to merge the data from the staging table over, then that particular one you might want to
Yeah.
have your logging, because you might want to be able to roll back the transaction altogether.
That's right. That's right. And it's still logging. You'll still have transaction control. What you will have is not that crash protection, right? So, but yes, I take what you're saying, and every time I create a staging table, I do it unlogged now. No logging, rather. Excuse me. There's another question.
So this was interesting because I've been following a project that the Wharton School is doing, and they have a massive data warehouse of financial data, research, and all of that. They use it for PhD research and things,
Right.
and then they also have customers who could use that data. And 10 years ago, they had, I think, like 12 different databases,
Yes.
and now they're down to 5, and Postgres is one of them.
Yes.
But one thing that they had to do is that some data needs to be refreshed every day, and some refreshes might take a few hours.
Right.
So the question always is like, what does a customer or user do while that data is unavailable?
right.
I'm just curious how you handle that.
Yeah. So that's a good question. For me, in the current role that I do at the History Lab, it's not too much of an issue because we have maintenance windows, right? But what I would recommend is, that's why actually looking at trying to scrunch those windows down into as small a period as possible is valuable, right? Even if you don't think at the outset you need it, right? Later on you may as things change, right? Again, it depends on your application. It may be in certain cases if you can have zero downtime, right? You'll need to do something more complex, right? And you'll need to maybe use those advanced techniques available in your database API or other things.
So yes, let's just say these hours, system is not available, data is not available.
Yes, hopefully it wouldn't be hours, but maybe for you could have minutes, windows where you can do it. So if the system's not being operated, accessed at night, let's say, for example, you could have a 15-minute window where things are done.
Excellent. Well, I think we are at time, so thank you very much.
Well, thank you. Thank you for taking the time and coming to the talk. It's a lot of fun.